As we continue our study of graphing, in Topic 6 of Chapter 2, we're going to look through all of these: continuity, the identity, squaring, cubic functions, square root, cube root functions, absolute value, piecewise defined functions, and this particular relation. All right, starting off, continuity. By this, it simply means when we plot the graph, and if we had a pencil or a pen that we were doing the graph with, do we have to lift the pen up off the paper and then continue it? So the idea of lifting it off the paper, this is a discontinuity. Keeping it on the paper to draw the full graph, that is a continuity. And there is the definition. So, as we look at this first example, if we were going to graph it, we would come down from infinity up in this direction. Our pencil would be on the paper, and then we would get to this point, and we'd stop. And in fact, that circle means we are stopping just before we reach the 2. Then we jump up and lift the pencil up off the paper and start here, and then continue. Now, interestingly, the domain of this, as we look at it, is coming from negative infinity out here, and it goes to this point, but because this is a hollow, it's not included on this line. But since this is a solid dot, it picks up and continues. So the domain of this would be from negative infinity to positive infinity. And the range is also the same. Now, is this a function? Well, if this were a solid dot, it would not be, because it wouldn't pass the vertical line test here. But since it's hollow, it does pass the vertical line test and is a function. But it's not continuous. It is a discontinuity. Now, for this one down here, as we take our pencil, it stays on the paper throughout the graphing of our graph. And that would be continuous. That shows continuity. Now, as we do this line, and we get up to 3, we see there's a hollow dot at 3. This indicates it is not continuous and shows a discontinuity. You had to lift your pencil up. 3 is not in the set. Okay. And they're showing you in interval notation what it would look like. In letter B, it would come from negative infinity, go up to 3 and stop just before 3. And it would then continue. Now, normally we put like a union symbol there, but that would be the domain of this one. Okay, now what we're doing is we're going to sketch various graphs depending upon what they ask us to do, and then what it looks like, and then its domain and its range. Now, for this first one, and we've done this already in a previous chapter, we said we could take this f of x, change it to a y, and we say y equals x. So again, the slope of it is 1. Your y-intercept is 0. So you graph it by putting a dot at 0, and then you can go over 1 for the slope and up 1, and that gives you 2 points that you then extend in both directions. And again, there's an infinite number of points along this line. So the domain of it, we said, was from negative infinity to positive infinity. And the range is also from negative infinity to positive infinity. Now, if you didn't use the slope-intercept form to graph it, you could plot some points. And again, whatever y is, that's what x is. And it looks like that in a t-chart. And if you were to put this in your graphing calculator, this is what it looks like. Okay, that was sort of an easy one to start us off. Now, the next function, as we look at it, again, we can change the function symbol to y. Y equals x squared. And again, if you plotted points in a t-chart, you would get this particular shape where, again, there is no y-intercept here. So our y-intercept is at 0. And keep in mind it's decreasing to this point and then increasing. At the point where it stops decreasing and starts to increase, we call that the vertex. In this case, it's the lowest point of your parabola. Now, notice the domain of it would be x values, where in a sense this goes off to negative infinity in that direction and positive infinity in that direction. So there's the domain in interval notation. And when we think of our range, we are starting at 0. And 0 is included in the set, so we use a bracket, and it's going up to positive infinity. So anytime you see an equation like y equals x squared, all you have to think of is it's basically this shape, but this goes through 0. And again, I would take notes on this and study them, and then kind of make little reference cards or whatever that would serve as something you could use to study to show you these various graph forms depending on the equation. Because in MATLAB you're going to be asked to pick out things, and in some cases to draw them. Now in this next one we have the function of x is equal to x cubed. This is a cubing function. And we also, in a sense, get a reflecting type of situation, that if you were to fold this down, bring this top part, fold it over, this line would coincide with this line. So there is sort of a reflection. Now notice what's happening here. This is coming up from negative infinity in our range and going up to positive infinity, as we see here. And then in a sense, it eventually gets over to negative infinity for the domain and the range. This is very, very typical of what your y equals x cube function looks like. So again, one to put in your notes so that you have this reference. Now, another one that's very famous is the square root and cube root function, where here we have the function of x is equal to the square root of x. Now, note that we had said that under a radical sign that has an index number of 2 here, that is, we don't write it when it's 2, it's the square root, can you have a negative value? And the answer is no. So the lowest value you could have under this would be, it has to be greater than or equal to 0. We talked about that earlier. So our first number in our t-chart has to be 0. So it's going to start at 0, and it takes this particular shape. This is the graph of the square root of x. And its domain, it starts at 0, and it goes to positive infinity. And its range, in this case, is the same. It's starting at 0 and eventually goes up to positive infinity. And there is the graph. Again, I think these are a little bit easy, but for some of you, you need to take the notes and then keep matching what the function is to its graph. Later, we're going to play with these graphs a little bit, so this is really some basic material you need to be familiar with. Now, when we do the cube function, here our index number is 3. Because it is an odd index number, we are allowed to have negatives under the radical. And notice what happens, that along with the typical square root function, because we are allowed to have negative functions, we get the graph continuing to the negative side. And there's the typical one. Now remember, if you kind of twisted that around, and it went up this way and went down this way, this would be the x cubed. But in this case, where it's sort of close to the y-axis, the x-axis, the other one's closer to the y-axis, then this is the cube root function. Okay, now what are the domain and range? Well, there's our domain, again from negative infinity to positive infinity, and again for the range it's the same. And again, this is continuous. I don't know if we were stressing that, but again, we didn't have to lift our pencil off the paper while we were doing these. Okay, this is the absolute function values, where we have f of x is equal to the absolute value of x. And remember, this will always be a positive value. Absolute value is an operation that whatever is within the vertical lines, which is the absolute sign, indicates when it comes out of that, it will be a positive value. Okay? So let's go and take a look at some of these. If you do your t-chart and put in positive values here, remember it will always come out, these negatives will always come out as a positive. So in a sense, it's a reflection of what is on this side, but now to its negative value. So you always get these nice little V-shape diagrams. So whenever you see something like this, this is going to be an absolute function. So y equals the absolute value of x, and this is what you get. Notice we did this with y equals x, was a line that went up this way. But now, since they can't be negative values, this will always come out as positive. There's nothing in the bottom. It ends at 0. So our domain, our x values, can go from negative infinity to positive infinity, but our range starts at 0, and we use a bracket because it is included, and it will go to positive infinity. And it is continuous. We don't lift the pencil up off the paper. Now in this next type of function, we're going to say the absolute value, in this case of piecewise defined function, is defined by different rules over different intervals of its domain. So since it will be in pieces, you can probably imagine that it's going to be discontinuous. And here are some examples that we're going to work here shortly. And as we look at it, we see that we have a function of x, which could be y, is equal to this with these qualifiers. And then you have this equation, or part of the function, with this qualifier. And over here, something similar. Now we're not going to be using the graphing calculator, so we'll sort of pass this one up. And we'll look at this example right here. Now in the strategy for doing piecewise graphs, or recognizing them, because yours will probably be multiple choice, which is which, we have the function y equals this, which is I've written here, and it has this qualifier. So what you are to pick up on is what points do you put here for x? Well, it says here x is less than or equal to 2. So we know we can have a 2, but it says x is less than or equal to 2. So what would be another number? Well, a 1. Another number would be a 0. And then we would continue this down. But this gives you enough to where you will anchor your graph. It's going to start here and then continue this way. So what is this? Well, negative 2 times 2 is a negative 4. Negative 4 plus 5 is 1. So when x is 2, this output is 1. Now how about if this is a 1? Negative 2 times 1 is negative 2, plus 5 is 3. And if this is a 0, this will be a 5. So we'll get to graph these in a moment. Now in this one, we say x is greater than 2. So 2 is not really in the set. So I'm going to put like a circle around there. We're going to put a circle on our graph where this 2 is, because it's not included in the set. And then it's greater. So we can use 3 and 4. So if x is 2, 2 plus 1 is 3. If x is 3, this is a 4, and this is a 5. Now we're going to go over and put it on our graph. Well, here this one is included. X is 2, y is 1. So x is 2, y is 1. And we put a dot there. That's where we're starting. And then if we plot these other points, you get this line. These other points, 1 and 3, 1 and 3 is right there. And then 0 and 5 is right there. And this continues. Okay, then we do this one. Now, x is 2, y is 3. So we go over to 2, and we go up to 3. But remember, this is not included in the set. So we put a circle there, which is what they have there. And then 3, 4 is right there. 4, 5 is right there. So you have set up what is called a piecewise graph using this technique, writing the function, writing the qualifier, and then picking out points that suit this, that gives you this graph. Again, the other function, looking at the qualifier, picking out points, remembering if it's just a less than or greater than here, that point is not included, but it tells you sort of where to anchor your graph. Okay? Now, is this continuous? No. This is discontinuous, and this is a piecewise function. Now, notice in this one, this is also piecewise. They're giving you this with its restriction and this with its restriction. And when you plot this first one, it looks like so. The second one is a portion of a parabola. Notice it's not a straight line, but sort of a curve. When your exponents are only to the first power, you get a straight line. When you have something to the second power, you get a parabola or curve. And notice that this x squared is negative. That's the reason it opens, in a sense, downward. More of that later as well. Okay, we're now going to look at what is called the greatest integer function. And this is written in a kind of a funny way here. It's like double brackets. This pairs every real number with x with the greatest integer less than or equal to x. Now, what does this mean? Well, if this is 5.5, then its greatest real integer less than or equal to x would be 5. And I was looking for some background on this, and actually I came up with this that I thought was sort of interesting, and we'll include it here. This is from YouTube. Let's check it out.
Hi there. One of my favorite functions is the greatest integer function. What's this? You've never heard of the greatest integer function? So the greatest integer function, which we denote by these funny bracket thingies, takes a real number x and outputs the greatest integer that's less than or equal to x. Recall that the integers are the set containing the positive whole numbers, 0, and the negative whole numbers. And if you want an example of this, well, positive whole numbers are numbers like 1, 2, 3, 4, 5, 6, 7, and so on. 0, well, we all know what 0 is. 0 is just 0. And negative whole numbers are numbers like negative 1, negative 2, negative 3, negative 4, and so on. So any function from the real numbers to the real numbers can be plotted. Let's go ahead and plot the greatest integer function. So here we have a plot of the greatest integer function. Let's see if we can explain why the plot looks the way it does. So consider the number 0.5. When we evaluate the greatest integer function at 0.5, we get 0, because 0 is the greatest integer that's less than or equal to 0.5. Let's look at the graph again. So see, 0.5 has a y value of 0, so the greatest integer sends it to 0. Let's do another example. So now, instead of 0.5, let's look at 2. What's the greatest integer that's less than or equal to 2? So that's what this symbol means. It means you find the greatest integer that's less than or equal to 2. Well, this is equal to, well, the greatest integer that's less than or equal to 2 is clearly 2. And if we look at our graph again, go over to 2, this whole means that we ignore it, and we see that our function's value is in fact 2. And let's do one more example. How about negative 3? Okay, so what's the greatest integer that's less than or equal to negative 3? Well, let's see. The greatest integer it's going to be negative 3 again. So let's look at the graph. So here we go. So negative 3, it's an integer itself, and it is the greatest integer that's less than or equal to negative 3. So now we know the greatest integer function. It's really just a function that rounds down. So here's the definition of the greatest integer function again. No, it's not really a formula. It's more of a concept. Remember, all functions are mapping such that for every value in the domain, there is exactly one value in the range. And here is the plot of the greatest integer function.
Now, as we look at this is a step graph that we will see in our textbook here in just a moment. So we thank this fellow for his contribution to what we have been doing, and we'll get back to what we do. So all this is showing that anytime you have a value of x, you will round down to get the greatest integer function. And this is something we'll be working with. And it gives rise to this step diagram. Notice it is discontinuous, but the domain is all real numbers. Now, graphing the greatest integer function, and here the author makes a t-chart, but makes it sort of sidewards. And here are your x values as we see them, and our y values as we see them. And it looks a little confusing, but when we have in this formula, when we put a 0 in there, our y is 1. When we put a 1 in there, it's 1.5. Well, actually a half first. Well, let's see if what I've done over here helps a little bit. So here are our points that we have for x. We're going to put it into our function, the greatest integer function. And when we put x is 0, 1/2 of 0 is 0. So this comes out as 1. And the greatest, again, we're saying integer less than or equal to x is 1. So this becomes a 1. Now, in this case where we have 1, we end up with 3/2. The integer less than or equal to x, the greatest one, is, again we're rounding down, will be 1. Now here when we put a 2 in there, this becomes 1 plus 1 is 2. So the greatest integer, well, the greatest integer less than or equal to x is 2. And then we put this here as well. If we put a 3 in there, the greatest integer, when we put the 3, we get 3 halves. Adding it to 2 halves gives us 5 halves, which is 2.5. The greatest integer, again we have to round down, is 2. And then if we put a 4 in there, this becomes a 4 over 2 is 2, plus 1 is 3. And then it continues. So there is a pattern. Like for 2 integers here, we get a 1. 2 integers here, we get a 2. And for 2 integers here, we get a 3. The next one would be a 3. And we see that when we do the diagram of it, that this is a step diagram, or a step graph, and it goes from a particular point where that is a value up to a hollow, where again that's just sort of where it ends, but it doesn't reach it because the one above it is the one that is where that next line starts. So let's take a look at applying this example here, applying a greatest integer function. Now I also looked at the video that the author has done, and that's very good too, and you get to those I guess by clicking on this little video symbol here in your textbook. And in MathLab they will have a link to it as well. But what you're doing is you want to deliver a package, and this company will charge $25 for the first up to 2 pounds. So you're starting there, and you're up to 2 pounds, you're paying $25. Then if it's over 2 pounds, again, you start there, but it's sort of anchoring at that. That's why that's hollow. And then it continues where you would pay $3 more. So that'd be $28. And then $3 more would be $31. And this type of thing. So this is your step diagram. Now notice that the domain of this would start at just beyond 0. Because if you have 0, you don't have a package. And you're paying the $25. So it goes from a parenthesis and then theoretically on to infinity, but we're not going to have trucks big enough to carry that. Anyway, okay, let's go on. I think we're getting toward the end here. Oh yes. How about this last one where we have x equals y squared? Now, I think we mentioned this before, that if we were going to solve this, we would have y squared equals x. And then we take the square root of this side, but in order to get both possible results, we have to take plus or minus the square root of x. Now keep in mind that when we did the square root of x, we got this. That was its positive value, and then its negative value is just its reflection down below. And the domain, again, is at 0, going to positive infinity. Keeping in mind this is not a function. This does not pass the vertical line test. And range is from negative infinity to positive infinity. And again, make a little reference somewhere so you can see what this function looks like in a graph. And that completes our lesson.